Welcome to this lecture on reducible second-order ordinary differential equations. Imagine trying to carry a heavy two-story box up a flight of stairs. It is bulky, awkward, and incredibly difficult to manage all at once. But what if the box is designed so that the top half can be detached? You could carry the bottom half first, then go back for the top half, making the task much easier. In calculus, a second-order differential equation is like that heavy box because it involves the complex second derivative. Today, we will learn how to detach these problems into smaller, lighter pieces. Now that we understand the goal, let us look at what makes an equation reducible. A reducible second-order ordinary differential equation is a special type of equation that involves a second derivative, but it lacks either the dependent variable, usually called y, or the independent variable, usually called x or t. When an equation is missing one of these two specific letters, we can introduce a new temporary variable, typically called v, to represent the first derivative. By substituting this new variable into the original equation, the second derivative drops down to a first derivative. This clever trick reduces the heavy second-order problem into a much easier first-order problem that we already know how to solve. This brings us to our first specific scenario. We call this case 1, where the dependent variable is missing. In most problems, the dependent variable is the function we want to find, often written as y. If you look at your differential equation and notice that the plain letter y does not appear anywhere, you are dealing with this exact case. The equation will only contain the independent variable x, the first derivative, and the second derivative. To solve this type of equation, we introduce a substitution by defining a new variable v. This is a strategic move designed to lower the overall order of the differential equation, making it look and behave like a simpler problem. Let us formalize this concept mathematically. The formula on screen represents the general structure of a second-order differential equation, where the dependent variable y is missing. The capital letter F denotes the mathematical relationship connecting the terms. Inside the parentheses, we only see the independent variable x, the first derivative y prime, and the second derivative y double prime. Notice that the plain letter y is completely absent. When you encounter an equation in this exact form, it signals that you can use our standard substitution trick. By replacing the derivatives, the intimidating second derivative will completely vanish from the problem, leaving you with a standard first-order equation. Before we move on, let us see this with a concrete example. We are given the equation x times y double prime minus y prime equals 0. We are asked to find the general solution. First, we inspect the equation and clearly see that the dependent variable y itself is completely absent. Because y is missing, this perfectly fits our first case. We proceed by setting up our standard substitution. We define a new temporary variable v to be exactly equal to the first derivative y prime. Consequently, the derivative of v with respect to x equals y double prime. Plugging these into our original problem, we transform it into a standard first-order differential equation involving only x and v. Continuing with our transformed equation, our goal is to isolate the derivatives and group the matching variables together. We start by adding v to both sides, separating it from the derivative term. Then, we divide to gather all v terms on the left and all x terms on the right. Because the variables are now completely isolated, we are mathematically clear to integrate both sides independently. We apply the integral sign to both sides. Integrating 1 over v gives the natural logarithm of v, and integrating 1 over x gives the natural logarithm of x. We also add our first constant of integration c1, which represents any arbitrary number lost during the initial differentiation. Now we will find our final answer. By raising the mathematical constant e to the power of both sides, the natural logarithms cancel out, and we solve for our temporary variable v, getting v equals c1 times x. However, we must remember that v was just a stepping stone. Our ultimate goal is to find the original function y. We reverse our initial substitution by replacing v with the first derivative of y with respect to x. This brings our original dependent variable back into the spotlight. We are left with a very simple direct integration problem. Applying the basic power rule, we arrive at a final general solution, which includes two arbitrary constants, as expected for a second-order equation. Now that we have used this formula, let us understand where it comes from. This derivation establishes exactly how the substitution lowers the order of the equation. We start with the general mathematical representation, where y is missing. We define our new variable v to be exactly equal to the first derivative of y with respect to x. Because v is already the first derivative, differentiating it once more naturally gives us the second derivative of y. This provides us with a direct replacement for the highest order term. Substituting these back, the intimidating second derivative completely vanishes, proving that the equation successfully reduces to a standard first-order form. This brings us to our second category of reducible equations. We call this case 2, where the independent variable is missing. In many physical problems, the input variable is time or position, often written as x or t. If you inspect your equation and notice that this independent variable is completely absent, you are dealing with case 2. The equation will only contain the dependent variable y, its first derivative, and its second derivative. Because the input variable is missing, we cannot use the standard derivative substitution we just learned. Instead, we must rely on a clever trick involving the chain rule from calculus to bridge the gap between the variables we have and the variables we want. Let us look at the mathematical structure for this second case. The formula on screen represents the general structure of a second-order differential equation where the independent variable x is completely absent. Inside the parentheses, we only see the dependent variable y, its first derivative y prime, and its second derivative y double prime. When you see an equation in this form, it tells you that a direct substitution of x will not work. We still introduce a temporary variable v for the first derivative, but finding a replacement for the second derivative will require a different approach to completely avoid the missing variable x. Before we derive the chain rule trick, let us see it in action with a concrete example. We are given the equation y times y double prime plus y prime squared equals 0. If we inspect the equation carefully, we see the dependent variable y and its derivatives, but the independent variable x is completely missing. This falls into our second category. We set v equal to the first derivative. For the second derivative, we use our special chain rule substitution, replacing y double prime with v times the derivative of v with respect to y. Substituting these expressions back in, we successfully reduce the intimidating second-order equation into a much friendlier first-order equation. Continuing with our solution, our next objective is to solve this new first-order equation by separating the variables y and v. We start by subtracting v squared from both sides. To simplify further, we divide both sides by the variable v, assuming v is not 0. This reduces the power of v on the right side, making the equation much cleaner. We then divide by y and multiply by the differential dy to achieve complete separation. Now everything related to v is on the left and everything related to y is on the right. We place an integral sign on both sides, which results in standard natural logarithm functions, plus our first constant of integration. Let us find the final answer for this example. We exponentiate both sides to remove the natural logarithms. The negative sign in front of the logarithm of y means that y moves to the denominator, giving us v equals c1 divided by y. We must now remember that v was only a temporary placeholder. We replace v with its true identity, the derivative of y with respect to x. This brings the missing independent variable x back into our equation. We separate the variables one last time, multiplying by y and dx. Integrating both sides using the standard power rule gives us our implicit general solution, which defines a family of parabolas. Now that we have successfully used the chain rule substitution, let us understand exactly where it comes from. This chunk of the proof establishes how we can represent the second derivative without using the missing variable x. We start by writing the second derivative, y double prime, as the derivative of our temporary variable v with respect to x. Because we want to eliminate x entirely, we apply the chain rule from calculus. We expand the derivative of v with respect to x as the derivative of v with respect to y multiplied by the derivative of y with respect to x. This expansion is the crucial step that bridges the gap. Continuing with our derivation, we can simplify our chain rule expansion by recognizing a familiar term. The second part of our expanded expression is the derivative of y with respect to x. This is exactly how we defined our temporary variable v in the first place. By substituting v into the expression, we get our final replacement for the second derivative. We have successfully expressed y double prime entirely in terms of v and y, completely avoiding the missing variable x. This brilliant mathematical trick is what allows us to reduce the complexity of the problem and solve it. Let us take a moment to look at this flowchart, which visually summarizes everything we have learned so far. At the top, we start with a second-order differential equation. The diagram splits into two distinct parts based on a simple check: which variable is missing. If the dependent variable y is missing, we follow the left path and use the direct substitution. If the independent variable x is missing, we follow the right path and use the chain rule substitution. As the diagram shows, both paths ultimately lead to the exact same goal: solving a simpler first-order equation for v and then integrating one last time to find our final function y. Why does this reduction technique matter in the real world? It is absolutely essential in physics and engineering, particularly when dealing with Newton's second law of motion. Newton's law states that force equals mass times acceleration, and acceleration is the second derivative of position. Often, the forces acting on an object, like air resistance or friction, depend only on the object's velocity and not on its exact position. In these cases, the position variable is missing from the equation, making it a reducible second-order problem. By reducing the equation, engineers can first solve for the object's velocity, which is critical for safety and design, before finding its final position. To summarize our lecture, reducible second-order differential equations are complex problems that hide a convenient shortcut. The most important step is identifying whether the dependent or independent variable is missing. If y is missing, we use a direct substitution. If x is missing, we use the chain rule trick. In both cases, the goal is to transform a difficult second-order problem into a manageable first-order problem. We solve for the first derivative temporarily and then integrate one final time to find the original function. Mastering this technique provides a powerful tool for breaking down intimidating mathematical models into solvable steps. You now have the skills to tackle these equations with confidence.